Hello and welcome to Lecture 11. This week we're going to start talking about our final chapter, Chapter 7. We will talk about inverse functions and their derivatives, natural logarithms, and exponential functions. After today's lesson, there will only be one lecture remaining. First, let's talk about inverse functions and derivatives of inverse functions. What is the opposite of adding 3 to a number? That's the same as saying what is the inverse of the function f, which maps from, let's say, z to z and has the formula f of x is equal to x plus 3. Well, we know the opposite of adding 3 is subtracting 3. So the inverse of our orange function is this green function, which maps again from z to z, from the integers to the integers, and has the formula f inverse of x is equal to x minus 3. Now, you will note that if we do orange function first and then green function, we get back to where we started from. Or if we did green function first and then we did the orange function, then again, we would just get x. That's what an inverse of a function means. One thing to note before I go on, the reason that they're existing an inverse is because every one of these numbers has one and only one arrow pointing towards it. So that's how we know how to go backwards. Some functions have an inverse. For example, the function g, mapping from the closed interval from 0 to 3 to the closed interval from 0 to 9, g of x is equal to x squared, has the inverse, g inverse of x is equal to the square root of x. Now note the domain of g is the interval from 0 to 3, and that's the same as the range of g inverse. Note that the range of g, closed interval from 0 to 9, is the same as the domain of g inverse. It doesn't matter which function we do first. If we do the square function first, let's say we take the number, square it, and then take its square root, we get back to 4. Or we'll do the other way around. Let's start with the number 9. First, square root it and then square it, and we get to 9. There's a typo there. But some functions do not have an inverse. For example, the function h, which has domain closed interval from minus 3 to 3, h and has the formula h of x is equal to x squared, does not have an inverse. Why? Well, 2 squared is 4 and minus 2 squared is 4. So what do we define h inverse of 4 to be? Should h inverse of 4 be 2 or minus 2? Functions can have only one value, so that means h inverse does not exist. Why does it not exist? Why does h not have an inverse? Well, if we look at a picture, there's 2 arrows pointing towards 4. It's not like the previous picture where each number had one and only one arrow pointing towards it. This number 4 has 2 arrows pointing towards it. That brings us on to this idea of one-to-one functions. Intuitively, a function is one-to-one if each number in the target has at most one arrow pointing towards it. Or to say it another way, 2 different arrows point to 2 different numbers. In terms of the equations, a function f is called one-to-one or injective on a domain D if this rule is true. Anytime we have 2 different numbers, x1 and x2, we must always have that f of x1 is different from f of x2. That's the same as saying two different arrows point to two different numbers. Some examples. The function x cubed is 1-to-1 on any domain. It doesn't matter which domain we choose, it's always going to be 1-to-1. The square root function is 1-to-1 on the closed interval from 0 to infinity. Why? Because we know that if x1 is not equal to x2, then the square root of x1 is not equal to x2. But x squared, looking at this picture now, is not 1-to-1 on R, because, for example, -1 squared is the same as 1 squared. And looking at the fourth picture, sine x is not 1-to-1 on the domain closed interval from 0 to pi, because sine pi over 6 is a half, and sine pi, 5 pi over 6 is also a half. However, if we make the domain smaller, so if we're just looking at this part, sine x is 1-to-1 between 0 and pi over 2. Now you would have noticed perhaps from the previous pictures there's some horizontal lines here. The 1-to-1 functions, the horizontal line intersects the graph at most one point. Functions which are not 1-to-1 have a horizontal line intersecting them at 2 or more points. The horizontal line test for 1-to-1 functions says a function y equal to f of x is 1-to-1 if and only if its graph intersects each horizontal line at most once. So first picture, there's one intersection, must be 1-to-1. Second picture, one intersection. One point where the line crosses the graph, must be 1-to-1. Picture 3, there's 2 points where the line intersects the graph, so it's not 1-to-1. And picture number 4, again, there's 2 points where the line intersects the graph, so the function in picture 4 is not 1-to-1. Now that we understand 1-to-1 functions, we can start talking about inverse functions. Suppose that f is a 1-to-1 function on the domain D and has range R. Then the inverse function is defined by this rule. F inverse of B is equal to A if we know that FA is equal to B. The domain of f inverse is R, that's the same as the range of the function we started with, and the range of f inverse is D, that's the domain of the function that we started with. This symbol, f to the power -1, we read this or pronounce this as f inverse. Now, we just know that if I wrote, for example, 5 to the power -1, we know that that means 1 divided by 5, but that's not what we're doing here. F to the power -1 means f inverse. F to the power -1 does not mean 1 divided by f of x. This is just a case of we don't have enough symbols so that each different idea can have its own symbol. We have to repeat symbols sometimes. To the power -1 we can use for two different things in mathematics. Example 2 from your textbook. Suppose a 1-to-1 function, y equal to f of x, is given by a table of values. then we can make a table of values for x equal to f inverse of y just by turning this table upside down. For example, if y is 3, then f inverse of 3 must be 1. Why? Because f of 1 is equal to 3. So we're just turning the table upside down. Now, let me just note that if f inverse is the inverse of f, then we have two rules. F inverse composed of f of x is always just x for all x in the domain of f, and f composed of f inverse of y must be equal to y for all y in the range of f. Now let's talk about how we find the inverse of a function. And again, I've taken some pictures from your textbook. If we want to find the value of f at x, then what we do, if we only have the picture, is we start at x. So start just here. Then we go up to the graph, and then we go across until we get to the y-axis. And then we find the value of f of x. The graph of f inverse is just the graph of f, but with x and y swapped. To find the x that gave a particular y, we can do the opposite. What we could do is we could start at a y on the y-axis, go horizontally until we get to the graph, and then go downwards and we find the value of x. If we want to draw the graph of f inverse, and if we already know the graph of f, what we can do is we can just do the mirror image or the reflection about the line y equal to x. For example, if the blue curve is y equal to f of x, then we can do its mirror image to find the orange curve, sorry, the yellow curve, which is then the graph of f inverse. Swap the letters, swap the x and the y. The previous graph had a y here and an x here. So swap the places, just keep the yellow curve, and then we've got the graph y equals f inverse of x. So the process of going from f to f inverse, we can think of this as two-step procedure. First, we could solve the equation y is equal to f of x for x. That would give us a formula of the form x is equal to something. And then we're going to swap all the x's and the y's, and we would end up with a formula of the form y equal to something. So let's do an example like that. Find the inverse of y is equal to half x plus 1 expressed as a function of x. We're going to do these two steps. First, we're going to take our formula and we're going to rearrange it so that it's of the form x equal to something. And then step 2, we're going to swap x and y. Okay, so let's start with our equation, our formula, y is equal to half x plus 1. Multiply it by 2, 2y on the left, x plus 2 on the right. Subtract 2 from both sides to get 2y minus 2 is equal to x, and then just change it around so that x is on the left. The first part is x is equal to 2y minus 2. And then step 2, we're going to swap x and y. Everywhere I see an x, I'm going to write y. Everywhere I see a y, I'm going to write an x. Instead of x equal to 2y minus 2, swap the x and the y, we get y is equal to 2x minus 2. This is the formula for the inverse of the function that we started. The inverse of f of x is equal to half x plus 1 is f inverse of x is equal to 2x minus 2. And the graphs of these functions look like this. The blue line is the function that we started with, and the yellow line is the graph of f inverse, the inverse function. And again, you can see these two graphs are mirror images of each other if we do reflection about the line y equal to x. Imagine putting a mirror on this pink line. Let's do another one. Find the inverse of the function y equal to x squared for x greater than or equal to 0, expressed as a function of x. Step 1, we're going to rearrange our formula to get x equal to something, and then step 2, we're going to swap x and y. So here's step 1. Starting with y is equal to x squared, square root of both sides. Square root of y is the square root of x squared, which is equal to the absolute value of x. But remember, we're only doing this for positive x. So actually, we don't need the absolute value signs in. We just have equal to x. So for step 1, we have x equal to the square root of y. Step 2, swap x and y. Instead of x is the square root of y, we want to write y is the square root of x. And then we can answer the inverse of y equal to x squared for x greater than or equal to 0 is y is equal to the square root of x. And again, let me show you the graphs of these functions. This yellow curve is the mirror image of the blue curve if we put a mirror on the pink line. But think about this. If we're always doing the mirror image like this, then we must be able to relate the slopes of the graphs. We want a formula which relates the slope of y is equal to f of x and compares it or relates it to the graph of y is equal to f inverse of x. And we're going to create that formula like this. Remember, f composed of f inverse of x is always equal to x. F of f inverse of x is always equal to x. I want to differentiate both sides. The derivative of f inverse of x must be equal to the derivative of x, but the derivative of x is just 1. What is this thing on the left? How do we take the derivative of a function of a function? The answer is we use the chain rule. The derivative of f inverse of x by the chain rule, f prime of f inverse of x multiplied by the derivative of f inverse of x. And then divide both sides by f prime of f inverse, we get the formula that we want. The derivative of f inverse is 1 divided by the derivative of f, but the derivative of f calculated at the point f inverse of x. This is an important idea, so let's write this as a theorem. First of all, this is just me being careful. This is another way of saying don't have any weird functions. Suppose that f is defined on an interval I. Suppose that f prime exists on I. And let's suppose that f prime is always not equal to 0 on I. Why not 0? Because we don't want to be dividing by 0. Then f inverse is differentiable at every point of its domain. The domain of f inverse is the same as the range of f. And we have the formula that we just created on the previous slide. The derivative of f inverse is 1 divided by the derivative of f, but calculated at the point f inverse of x. In terms of Leibniz's notation, this theorem says df inverse dx at the point x equal to b is equal to 1 divided by df dx calculated at the point x is equal to f inverse of b. So we're not just dividing by its derivative, but we're actually calculating the derivative at a different point. Let's do some examples. The formula we're going to use is in the yellow box at the top. Let f of x be equal to x squared for x greater than or equal to 0. Find f inverse prime at 4. And I'm going to solve this two different ways. The first solution, we already know the inverse of x squared is the square root of x, and we already know that the derivative of the square root of x is 1 over 2 square root of x. Method 2, I'm going to use the formula in the yellow box, and we should get the same answer. Using the theorem, if f of x is equal to x squared, so therefore f prime of x is 2x, we calculate that f inverse prime is 1 divided by f prime calculated at f inverse of x. But f prime is 2x, so that's just 1 over 2 multiplied by f inverse of x. And f inverse of x is just square root of x. And that's the same as we did, that's the same answer that we got in method 1. So hopefully that is more justification that our formula in the yellow box is the correct formula. Either way, whichever way we do this, we can answer the question now. Find f inverse prime at 4. Replace x by 4, 1 over 2 root 4, that's 1 over 4. Let me show you the graph of this. The blue curve is y is equal to x squared. When x is equal to 2, the slope is equal to 4. The yellow curve is y is equal to the square root of x. And when x is 4, that's the equivalent place, the slope is 1 divided by 4. So look, slope 4 here, slope 1 divided by 4, because we're doing 1 divided by f prime. Let's do another example. Let f of x be x cubed minus 2 for x strictly greater than 0. Find the value of df inverse dx at x equal to 6, which is the same as f of 2, without finding a formula for f inverse of x. So we're told we can't do the same as method 1 in the previous example. We have to use method 2. We have to use the formula in the yellow box. So let's look at the formula in the yellow box. We want to calculate df inverse dx at x equal to 6. So we need to calculate df dx at x equal to 2. right? If we want x equal to 6 just here, then over here x must be f inverse of 6, and f inverse of 6 must be 2. So we're going to do df dx at x equal to 2, and then we're going to do 1 divided by this number. Well, df dx at x equal to 2, that's 3x squared at x equal to 2, or 12. And then we're going to do 1 divided by 12 to get the answer. df inverse dx at x equal to 6 is 1 divided by df dx at x equal to 2, or 1 divided by 12. Let me repeat the ideas here. We're asked to calculate df inverse dx at x equal to 6. So looking at the formula in the yellow box, we want b equal to 6. Over on the right side, again, b is equal to 6. We want f inverse of 6, which is equal to 2. So we want to calculate 1 divided by df dx at x equal to 2. That's 1 divided by 12. And I'll show you the graphs of these functions. The blue curve is y is equal to x cubed minus 2, the function we started with. When x is equal to 2, the slope is equal to 12. The yellow curve is our inverse function, and the slope of the inverse function at x equal to 6 is then 1 divided by 12. Our second section for this week's lesson is about natural logarithms. I'll start with the definition of the natural logarithm. The natural logarithm is the function ln, which has domain, the open interval from 0 to infinity, and target, the real numbers. And it's defined using this formula. In this course, we're going to define it this way. Other mathematicians might define it using a different definition, but this is the one we're going to use. ln of x means the integral from 1 to x of 1 over t dt. I think we need a picture. Here's the graph of 1 over t, and we're interested in the area underneath this graph between 1 and x. And as x increases like this area is going to increase, so ln of x is going to increase like this. Well, this is the picture if x is greater than 1. What if x is less than 1? If x is less than 1, then we're going to be integrating from 1 to x, but that's the same as minus the integral from x to 1. So here I'm going to be drawing the integral from x to 1, and then ln is going to be minus this. As x gets closer to 0, we can see this area is getting bigger, so minus this area is getting more and more negative. Some values taken from your textbook. Remember, this is only defined for x strictly greater than 0. The domain of ln x is the open interval from 0 to infinity. So ln of 0 is not defined. Forget about that. if we put in these values of x and then calculate this integral, we get approximately these values of ln of x. Now, you'll notice that if we want ln of x is equal to 1, then that number is going to be somewhere between 2 and 3. And this is an important number. There's an important number between 2 and 3 where the natural logarithm is equal to 1. And this important number is called the number e. The number e is the number which satisfies ln of e is equal to 1. Or in terms of area under the graph, e is the special number such that the integral from 1 to e of 1 over t dt is equal to 1. We'll come back to talk about this number later. First, let's talk about the derivative of the natural logarithm. Well, the natural logarithm is defined to be an integral. And if you remember the first part of the fundamental theorem of calculus, that told us how to calculate the derivative of an integral. The derivative of an integral from a to x of f of t dt, all we do is we take the integrand f of t and replace the t by an x to get f of x. Well, using that idea, the derivative of ln of x, that's the derivative of the integral from 1 to x, 1 over t dt, all we need to do is we take out integrand 1 over t and replace the t by an x. The derivative of ln x must be 1 divided by x. Taking that and using the chain rule, if u is a differentiable function of x, and if u of x is greater than or equal to 0, then it follows by the chain rule ddx of ln u is ddu of ln u multiplied by du dx. So that's 1 divided by u du dx. The next example is going to use this formula. Part A, first of all, this is another one taken from your textbook. The derivative of ln 2x, here we have u equal to 2x. That's 1 divided by u multiplied by d dx of u. So 1 over 2x multiplied by d dx of 2x, 1 over 2x multiplied by 2, or 1 over x. Or we could use this formula for the derivative of ln of x squared plus 3. Same idea, but now we're going to use u is equal to ln of x squared. Sorry, say that again. Now we're using u is equal to x squared plus 3. So we're going to have 1 divided by u, 1 over x squared plus 3, multiplied by du dx, or d dx of x squared plus 3. And then after we've done that derivative and simplified it, we get 2x over x squared plus 3. We could also do that with u equal to the absolute value of x. What we have is d du of ln u du dx. That's the chain rule. But what is the derivative of the absolute value of x? The derivative of the absolute value of x is x divided by the absolute value of x. So we get 1 over u, that's the derivative of ln u, multiplied by x over the absolute value of x, or 1 over absolute value of x multiplied by x over absolute value of x. Absolute value of x squared is the same as x squared because it's positive. X is cancelled and we end up with 1 over x. So that means 1 over x is the derivative of ln x on the domain x strictly greater than 0, and it's also the derivative of ln minus x on the domain x is less than 0. Let's talk about some properties of the natural logarithm. For any numbers b and x, which are any positive numbers b and x, the natural logarithm satisfies these 4 rules. ln of bx is ln of b plus ln of x. ln of b divided by x is ln b minus ln x. ln of 1 divided by x is minus ln of x, and ln of x to the power r is r ln x for rational numbers r. For example, ln 4 plus ln sine x, using the product rule, that's the same as ln 4 multiplied by sine x. Or b, ln of x plus 1 divided by 2x minus 3. By the quotient rule for the natural logarithm, that's the same as the thing on the top. So ln of the thing on the top, ln x plus 1, minus ln of the thing on the bottom, ln 2x minus 3. And then part C, ln of 1 over 8. Well, 1 over 8 is the same as 8 to the power minus 1. And by the reciprocal rule, the minus 1 we can take outside. So we get minus ln of 8. 8 is 2 cubed. The 3 we can also take outside. Minus 3 ln 2. Okay, so let's prove some of these rules. I want to prove that ln of bx is ln b plus ln x. Well, the first thing to note is, and we've done this already with 2, I think it was, but I'll leave it for you to check. The derivative of ln bx is b divided by bx. Cancel the b's, we get 1 over x. But that's the same as the derivative of ln x. We have 2 different functions, ln of bx and ln of x, which have the same derivative. And we've looked at this idea earlier. If you go back to the second corollary of the mean value theorem, all of the way back in, where was it, lecture 6. If 2 functions have the same derivative, then one function must be equal to the other function plus some constant c. So because ln bx and ln x have the same derivative, we must therefore have ln bx is equal to ln x plus some constant c. But what is this constant c? Well, we can find the value of the constant c by replacing x by 1. Because then we have ln of b multiplied by 1 is equal to ln of 1 plus c. But on the left, it's just ln b. ln of 1 is 0. So on the right, we just have c. So ln b must go in just here. And then we're finished. Then we've proved the formula that we want. We've proved the product rule for a natural logarithm. ln of bx is equal to ln x plus ln of b. Let's prove another one. Let's prove that ln x to the power r is equal to r ln x, assuming that r is a rational number. Well, what we can do is we can start with the chain rule and do this calculation. I want to differentiate ln x to the power r with respect to x. I'm going to do the substitution u is equal to x to the power r. So I have d dx of ln u. By the chain rule, that's d du of ln u multiplied by du dx, but the derivative of ln u is 1 over u. So it's 1 over u du dx. And what is du dx? Du dx, of course, is just r x to the power r minus 1. Most of these terms will cancel, and we just end up with r multiplied by 1 over x. But wait a minute, that's the same as the derivative of r ln x. So just as we did before, we have two different functions which have the same derivative. The derivative of ln x to the power r is the same as the derivative of r ln x. So therefore, one function must be equal to the other function plus a constant. What is the constant? Again, if we put in x equal to 1, we can find the value of constant. We can find that we get 0 is equal to 0 plus c, so the constant c must be 0, and then we're finished. That proves that ln x to the power r is equal to r ln x. Let's talk about the graph and the range of ln x. I've shown the graph earlier when I was giving the definition in terms of area under the graph of 1 over x. The graph of y is equal to ln x looks like this. What can we say about this? Well, the first thing is, because the derivative of ln x is 1 divided by x, and if x is positive, 1 divided by x must be positive. So ln x must be an increasing function. We can differentiate it again. The second derivative of ln x, that's the same as the derivative of 1 over x, is minus 1 over x squared, and that must be negative. So the graph of ln x must be concave down. And again, we can see that from the picture, but we've proved it now. Increasing and concave down. Now, remember, what does ln2 mean? ln2 means the area underneath the graph of y is equal to 1 over t between 1 and 2. And I can see from this picture that this blue area must be bigger than a half, say, because the area of this orange region is a half. So just from looking at this picture, I can say I must have ln of 2 is bigger than a half. But then that means ln of 2 to the power n, or n ln 2, must be bigger than n multiplied by a half, or n over 2. I'm going to take the limit of these two things I've underlined in orange. The limit of ln 2 to the power n must then be greater than or equal to the limit of n divided by 2. But we know that limit is equal to infinity. We have an increasing function. So ln x must have the same limit as ln 2 to the power n, which must be infinity. This is the proof that the limit as x tends to infinity of ln x must be equal to infinity. So even though the graph is concave down, it still keeps going up all of the way to infinity. If we do the substitution t equal to 1 over x, we can also prove this. I want to calculate the limit as x tends to 0 from the right of ln x, and I'm going to do the substitution t equal to 1 over x. So instead of doing ln of x, I'm doing ln of 1 divided by t. That's the same thing. And instead of x tends to 0 from the right, well, x tends to 0 from the right is the same as t tends to infinity. So that's the same as the limit as t tends to infinity of ln of 1 divided by t. Or the limit of ln t to the power minus 1, or the limit is minus ln of t, or minus infinity. This is the proof that as x tends to 0 from the right, the graph of y is equal to ln of x goes all of the way down to minus infinity. The y-axis is a vertical asymptote of this graph. As I think I've said before, the domain of ln x is the strictly positive real numbers, the open interval from 0 to infinity. And because we found the limits that are infinity and minus infinity, now we know that the range of ln x must be the whole of the real numbers. We've talked about the derivative of ln x. Now let's talk about the integral of 1 over u du, the indefinite integral of 1 over u. If u is differentiable and if u is not equal to 0, then the integral of 1 over u du is equal to ln absolute value of u plus c. And if u is equal to a function of x, then du is equal to du dx, or f prime of x dx, and then our formula becomes integral of f prime divided by f dx is equal to ln of absolute value of f of x plus c. We can use this to calculate integrals like this. Calculate the integral from minus pi over 2 to pi over 2, 4 cos theta divided by 3 plus 2 sine theta d theta. The idea here is we want to rewrite this integral in the form integral of du over u. We're going to do a substitution so that our integral looks like this. And the substitution we're going to use is, of course, I think, u equal to 3 plus 2 cos theta. But then du is 2 sine theta d theta. Well, we almost have that. That's going to make the top much easier. We need to do the limits of integration. Instead of theta is pi over 2 and theta is equal to minus pi over 2, we need to change these into limits for u. First of all, if u is equal to pi over 2, then u is 3 plus 2 cos theta, 3 plus 2 cos pi over 2. Cos pi over 2 is equal to there's a mistake here, of course. What am I doing? This should be sine, and therefore this one should be cos. This should be sine, and this one should be sine. Sine pi over 2 is 1, so 3 plus 2 times 1 is 3 plus 2, or 5. And 3 plus 2 sine minus pi over 2 is 3 minus 2, or 1. And then we're ready to do the substitution. The integral from minus pi over 2 to pi over 2, 2 times 2 cos theta divided by 3 plus 2 sine theta d theta is equal to the integral from 1 to 5 of 2 divided by u du. And then we've changed our difficult integral into an easy integral. This one we can calculate. Formula is in the yellow box at the top. An antiderivative of 2 divided by u is 2 natural logarithm of the absolute value of u. We have 2 ln 5 minus 2 ln 1, but ln 1 is just 0. So the answer to this problem is 2 ln 5. And that brings me to a nice point to take a break. We're going to take a 10-minute break, and we're going to continue at 3. And let's continue. Next, I want to talk about the integrals of tan x, cotan x, sec x, and cosec x. And to calculate these integrals, we're going to use this formula. Integral of 1 over u du is equal to ln absolute value of u plus c. First of all, let's talk about the integral of tan x. Remember, tan just means sine divided by cos. And I want to do integral of du divided by eu. So I need to do a substitution. And I'm going to do the substitution u is equal to cos x. Because then du is minus sine x dx. And so the integral of tan x, or the integral of sine divided by cos, is equal to the integral of minus du over u. We almost have exactly what is in the yellow box, just with an extra minus sign in. So of course that's minus ln absolute value of u plus c, or minus ln absolute value of cos x plus c. Minus ln absolute value of cos x is ln absolute value of cos x to the power minus 1 plus c, or ln 1 divided by absolute value of cos x plus c, but 1 over cos is just sec. So the formula is the integral of tan is ln absolute value of sec x plus c. We can do the same thing for the integral of cotan x, because cotan just means cos divided by sine. So exactly the same idea as before. We have divided by sine x, we'll do the substitution u is equal to sine x, and then the cos x is going to cancel out. But I'm going to leave details here for you to fill in. Please fill in the full details, and you will see, or you should be able to show, that the integral of cotan x dx is equal to minus ln absolute value of cosec x plus c. The next one's a little bit more difficult. I want to calculate the integral of sec x, and again I want to use the formula that the integral of du over u is ln absolute value of u plus c, but we need to do an extra step first. We're going to multiply and divide by sec x plus tan x, which I'm calling u. Why are we doing sec multiplied by sec plus tan? Well, look at the formulae in the yellow box. Remember, the derivative of tan is sec squared, or to say it another way, the integral of sec squared is tan, and the derivative of sec is sec tan, so the integral of sec tan is equal to sec. Okay, so let's do that. We're going to start with the integral of sec x dx, and we're going to multiply and divide by sec x plus tan x. Or think of it another way, that's sec squared plus sec tan divided by sec plus tan. Sec squared, that's the derivative of tan. I have a tan on the bottom. Sec tan is the derivative of sec, and I have a sec on the bottom. So that's why it's going to work. It's time to do a substitution, and we're going to use the substitution u is equal to sec x plus tan x. And when we do that substitution, this difficult looking integral simplifies down to integral of du divided by u. And of course, we know that. We know that that is ln of the absolute value of u plus c. Substitute back in. Our formula is that the integral of sec x dx is ln absolute value of sec x plus 10x plus c. For cosec, we do the same thing, but we're going to multiply and divide by something slightly different. We're going to multiply and divide by cosec x plus cotan x. Why are we doing that? Well, look at the formula in the yellow box at the top. The derivative of cotan is minus cosec squared. The derivative of cosec is minus cosec cotan. Oh, there's a mistake here. This should be cosec cotan. As we did before, now we can do the substitution. We can replace cosec x by cotan x by u. Everything on the top will cancel out and we'll just be left with integral of minus du divided by u. So that's minus ln absolute value of u plus c, or minus ln absolute value of cosec x plus cotan x plus c. Let's recap these four formulae. Integral of tan is ln absolute value of sec plus c. Integral of cotan is ln absolute value of sine plus c. Integral of sec is ln absolute value of sec plus tan plus c. Integral of cosec is minus ln absolute value of cosec plus cotan plus c. And these formula I will give you on the final exam. If you have to repeat this course, you might not be given them next semester. You might need to memorize them next semester. But this semester, I'm going to try giving you these in the exam. Let's use these formula. The integral from 0 to pi over 6, tan 2x dx. Well, I don't want a 2x here, I want a u here. So the first thing to do is to substitute u equal to 2x. We get tan u du divided by 2. And of course, we change the limits. Instead of 0 and pi over 6, we get 0 pi over 3. What is a half? Integral from 0 to pi over 3, tan u du. Remember, that's a half. ln, absolute value of sec u, calculated at pi over 3 and 0. Sec of pi over 3, that's 1 divided by cos of pi over 3, 1 divided by a half, or 2. What is sec of 0? 1 divided by cos 0, so that's 1 divided by 1, or 1. A half ln 2 minus ln 1, but ln 1 is just 0, so a half ln 2. Let's talk about logarithmic differentiation. This is another form of implicit differentiation, which we studied all of the way back in, when was it? Lecture 5. The idea is we're going to start with an equation we need to differentiate, and we're going to take ln of both sides of the equation. And then we're going to use implicit differentiation. So for example, find dy dx if y is equal to x squared plus 1, x plus 3 to the power half, divided by x minus 1 for x greater than equal to to 1. And we could use the quotient rule, but it would become very messy. It's going to be easier if we take ln of both sides here. We're starting with y is equal to x squared plus 1, x plus 3 to the power of a half divided by x minus 1. And we're going to put ln on both sides. It's going to be ln of y is equal to ln of x squared plus 1, x plus 3 to the power of a half divided by x minus 1. And the reason we're doing this is because then we can simplify the right-hand side. Remember, ln of a divided by b is ln a minus ln b. And ln of ab is equal to ln a plus ln b. Now that makes things a lot easier because now we can differentiate both sides. The derivative of ln y is equal to the derivative of this long thing. And this is the implicit differentiation bit, or the chain rule bit. On the left side, ddx of ln y is ddy of ln y multiplied by dy dx. So that's 1 divided by y dy dx. On the right side, again, chain rule. Derivative of ln x squared plus 1 is it's going to be 1 divided by x squared plus 1 multiplied by the derivative of x squared plus 1. So 2x over x squared plus 1. A half. Derivative of ln x plus 3 is just 1 over x plus 3. Derivative of x minus 1 is 1 over x minus 1. Multiply both sides by y, we get this. But we know y. Y is the function that we started with. So instead of what would become a difficult quotient rule problem, we've used logarithmic differentiation to find dy dx. And that's all I want to do about logarithmic differentiation. Instead, I want to move on to our third and final section for today's lesson. I want to talk about exponential functions. ln, which we've been talking about, is a one-to-one function. The domain of ln is the open interval from 0 to infinity, and the range of ln is the whole real numbers, so the interval from minus infinity to infinity. So that means there exists an inverse function. Let's call it, for now, let's call it ln to the power of minus 1, the inverse of ln. This green function must have domain, the whole real line, and it must have range, open interval from 0 to infinity. This inverse of the natural logarithm is called the exponential function, and we write it like this. exp of x, or e to the power x. And because it's the inverse of the natural logarithm, we have that e to the power ln x is x, and we have ln of e to the power x is x. Wherever they are defined. ln is defined for positive numbers, so the first equation is true for positive numbers. The second one is true for all x. What can we do with e to the power x? Well, first example, solve the equation e to the power 2x minus 6 is equal to 4 for x. What we're going to do is we're going to take the natural logarithm on both sides, and then we're going to rearrange. Start with e to the power 2x minus 6 is equal to 4, and put ln on the left and ln on the right. But ln and e of e, they just cancel out. Instead of writing ln of e, we can cross these out. We just have 2x minus 6 is equal to ln 4. 2x is 6 plus ln 4, or x is 3 plus a half ln 4. 3 plus ln 4 to the power of a half, that means square root of 4. The answer is x is equal to 3 plus ln 2. A line with slope m passes through the origin and is tangent to the graph of y is equal to ln x. What is the value of m? Well, let's suppose that this number is a. Let's suppose this line touches the graph when x is equal to a. So in other words, it touches at the point a ln a. We know that the derivative of ln is 1, ln x is 1 divided by x. So the slope of the graph at this point, and therefore the slope of this tangent line, must be 1 divided by a. So now we're looking for the line which passes through 0 and a ln a and has slope 1 over a. But the slope must be, let me clean this out. The slope, if we draw this triangle, must be height of the triangle divided by base of the triangle. The height is ln a, and the base is a. So the slope, which we've called m, must also be ln a divided by a. So we've said the slope is 1 over a, because that's the derivative of ln, and from the picture, the slope must be ln a divided by a. So we must have that ln a is equal to 1, we must have that a is equal to e, and therefore the slope of the line must be 1 over a or 1 over e. I'll leave that example for you to reread in your textbook. I want to move on to talking about the derivative and the integral of e to the power x. And I'm going to start with our equation. Ln of e to the power of x is equal to x, and I'm going to differentiate both sides. The derivative of ln e to the power x is equal to the derivative of x. On the left, I get 1 divided by e to the power of x, d dx of e to the power x. That's the chain rule. And on the right-hand side, the derivative of x with respect to x is 1. Rearrange this. The derivative of e to the power of x is e to the power x. This is very important. Let's write this as a fifth. The derivative of e to the power x is equal to e to the power x. This is the only function, apart from multiples of it, which has the rule that when we differentiate it, we still get the same function. We could do any number multiplied by e to the power of x, differentiate it, and we can get the same thing, but that's it. There are no other functions which have the special property that when you differentiate them, you still get exactly the same function. That means e to the power x is a very, very important function. Example 3 from your textbook. Let me go through very, very quickly because this is quite a simple example. E to the power of x, take the 5 outside, 5 times the derivative of e to the power of x, that's 5 e to the power of x. Chain rule here. Derivative of e to the power minus x ends up as minus e to the power minus x. Another chain rule. Derivative of e to the power sine x. E to the power sine x, because derivative of e to the power x is e to the power x, multiplied by derivative of sine x. So e to the power sine x multiplied by cos x. And then finally d. The derivative of e to the power of square root of 3x plus 1. Again, it's a chain rule question. We have e to the power u, so it's d du of e to the power u multiplied by du dx. So just e to the power root 3x plus 1, but then multiplied by the derivative of the square root of 3x plus 1. And you can finish that. Because when we differentiate e to the power x, we get e to the power x, we could do the opposite. Integration is the opposite of derivatives. If e to the power of x is the derivative of e to the power x, then e to the power x is also an antiderivative of e to the power x. So the integral of e to the power of x dx must be e to the power of x plus c. Another example from your textbook using this property. Which bit do I want to do? Just look at this part. 1/3 integral from 0 to ln 8 e to the power u du. That's just a third e to the power u calculated at ln 8 at 0 because e to the power u is an antiderivative of e to the power u. And I'll leave part B for you to read yourself. What can we say about e to the power of x? Well, as I said earlier, the domain is the whole of the real line, and the range is the strictly positive numbers. The limit as x tends to infinity of e to the power of x is infinity, and the limit as x tends to minus infinity of e to the power of x is equal to 0. Let's go through some laws of exponents. I'm not going to prove these laws. You can find the proofs in your textbook. Rule number 1, e to the power a, e to the power b is e to the power a plus b. E to the power minus x means 1 divided by e to the power of x. E to the power a divided by e to the power b is e to the power a minus b. And e to the power a all to the power b is e to the power ab. I want to move on up to talking about the general exponential function a to the power of x, where a is any strictly positive number, and I don't know what I was writing there. And x must be any real number. The exponential function with base a to the power x, is defined to be e to the power of x ln a. For x greater than 0 and for any natural number n, x to the power n is defined to be e to the power n ln x. I think that should be R. I'll check it later. Now that we have this definition, we can prove this theorem. For any x greater than 0 and any n in the real numbers, the derivative of x to the power n is n x to the power n minus 1. This is a formula we've been using for many weeks, but we didn't prove it for real numbers, we only proved it for rational numbers before. And we can say if x is less than or equal to 0, then the formula is also true, but as long as everything in the formula exists, as long as the derivative of x to the power n exists, as long as x to the power n exists, and as long as x to the power n minus 1 exists. This we're going to prove. First, if x is greater than 0, then we can calculate it like this, because x to the power n just means e to the power n ln x. And we know how to differentiate that. That's just e to the power n ln x multiplied by the derivative of n ln x. So just x to the power n multiplied by n over x, we get the formula that we expected. Now let's do it for strictly less than 0. We'll do x equal to 0 later. Now let's do x strictly less than 0. And we're going to assume that f prime, so we're going to assume that y prime, y, and x to the power n minus 1 all exist. And then we're going to use the formula ln of absolute value of y is equal to ln of absolute value of x all to the power n, or n ln absolute value of x. And we're going to differentiate this using implicit differentiation. Start with this equation, ln of absolute value of y is equal to n ln of absolute value of x, and differentiate both sides. What do we get on the left? Just y prime over y. What do we get on the right? N divided by x. But then y prime is n, y of x, and that simplifies to n x to the power n minus 1, which is what we expect. One more case to consider, and that's the case x equal to 0. If x is equal to 0, and we need to have n greater than or equal to 1 here for everything to make sense, we can use the definition of the derivative, the definition involving the limit. The derivative of x to the power n at 0 is, the limit as h tends to 0, of 0 plus h to the power n minus 0 to the power n divided by h, and we just end up with 0. Okay, but how do we differentiate x to the power x, assuming that x is greater than 0? We can't just use the power rule because we don't have x to the power n, we have x to the power x. But we can do the same thing that we did before, because x to the power x means e to the power x ln x. And if we differentiate this using the chain rule, e to the power x ln x multiplied by the derivative of x ln x, and I'll leave it for you to check, we get x to the power of x ln x plus 1. Let's briefly talk about this number e. Think back to before the break, we saw this number e must be somewhere between 2 and 3, but what is its value? Actually, we can calculate it as the limit as x tends to 0 of 1 plus x to the power 1 over x. Let's prove this formula. And we're going to prove it using the natural logarithm. F of x is equal to ln x. If fx is ln x, then its derivative is 1 over x, and f prime of 1 is then equal to 1. Now I want to use the definition of the derivative. 1 is equal to f prime of 1, but that means the limit as h tends to 0. Why limit? Because we want to end up with a limit. F at 1 plus h minus f at 1 divided by h. Now, we want to end up with limit as x tends to 0. So, and here, it doesn't matter which letter we use. We could use H or A or B or C, whichever letter we wanted. Let's say we use the letter X. So just taking that formula and replacing every H by X, it's still true. That's the limit as x tends to 0 of ln of 1 plus x minus ln of 1, but that's 0, divided by x. We get the limit of, as x tends to 0, 1 over x, ln of 1 plus x, but that's exactly what we wanted, isn't it? Almost. Limit as x tends to 0 of ln 1 plus x to the power 1 over x. ln is continuous. Anytime we have a continuous function, we can swap the limit and the continuous function. That's ln of the limit as x tends to 0, 1 plus x to the power 1 over x. I think you can see what we're going to do here. We're going to take the exponential of both sides, and then we're going to be finished. Taking the exponential of both sides, we get the formula that we required. If we choose a very, very small x, and then if we calculate 1 plus x to the power 1 over x, we can approximate e. And we can find that e is approximately 2.71828182845905. And then it goes on and on for the true value of e, because e is irrational. What is the derivative of a to the power x? Well, what does a to the power x mean? A to the power x really means e to the power of x ln a. We know how to differentiate that using the chain rule. We get a to the power of x ln a. But that's another reason why e is a special number, because if we put the number e in here, derivative of e to the power of x is e to the power of x ln e. But ln e is 1, so we just get e to the power of x. By the chain rule, if u is differentiable, then d dx of a to the power u must be a to the power of u ln a du dx for any a greater than 0. Or turning that around, we would have an integral formula. The integral of a to the power u du must be a to the power of u divided by ln a plus c. That's just chain rule or substitution. We can use those formulae to calculate these things. Part A is very simple. The derivative of 3 to the power x is 3 to the power x ln 3. For B, that's a chain rule question. The derivative of 3 to the power minus x, put u equal to minus x, and we end up with 3 to the power minus x ln 3 multiplied by the derivative of minus x, which just gives us a minus sign. C is also a chain rule question. The derivative of 3 to the power sine x, 3 to the power sine x ln 3 multiplied by the derivative of sine x, which is, of course, just cos x. And then D and E about integration. integral of 2 to the power x dx. Well, if we differentiate 2 to the power x, we need to multiply by ln2. The opposite of multiplying by ln2 is dividing by ln2. So 2 to the power x divided by ln2 plus c. And then finally, a substitution question. Using u is equal to sine x, integral of 2 to the power sine x cos x dx becomes integral of 2 to the power u du, and then it becomes easy. Logarithms with base a. Suppose a is a strictly positive number and a is not equal to 1. Then a to the power of x is a one-to-one function, and if it's a one-to-one function, that means it must have an inverse function. We can go further because the derivative of a to the power x is not equal to 0. Think back to the start of today's lesson. This tells us that this inverse function must be differentiable. And what do we call the inverse of a to the power x? We call it the logarithm of x base a. And we write this as log base a of x. Log base 2 of x is the inverse of 2 to the power x. If it's the inverse, then its graphs must be the mirror image like this. Just like for the natural logarithm, we have these two, or just for any inverse functions, we have our two rules. A to the power log base a of x is x. Log base a of a to the power of x is x. Have a look at this calculation. If y is equal to log base a of x, that's the same as saying a to the power y is x. Take the natural logarithm of both sides. Ln ay is equal to ln x. Powers we can take outside of the logarithm. This y can go outside. Y ln a is equal to ln x. So y is ln x divided by ln a. That is the proof that log base a of x is equal to ln x divided by ln a. Ln a is just a number. Ln x, this is a function that we've spent a lot of time studying. We know how to differentiate ln x. So now we know how to differentiate log base a of x. Derivative of log base a of u. That's the derivative of ln u divided by ln a, or 1 over ln a, because that's just a number, multiplied by ddx of ln u. By the chain rule, that's 1 over ln a, 1 over u, multiplied by du dx. And then one final slide is going to be using the formula in this box. This tells us how to differentiate ln a of u. For example, the derivative of log base 10 of 3x plus 1. Using the formula on the previous slide, 1 over ln 10 first, and then 1 divided by u, so 1 over 3x plus 1, and then multiply it by the derivative of 3x plus 1. or we can go backwards. The integral of log base 2 of x divided by x dx. That means 1 divided by ln 2 multiplied by the integral of ln x divided by x, because log base 2 of x just means ln x divided by ln 2. If we do the substitution u is equal to ln x, and I'll leave that for you to check, we just get 1 divided by ln 2, integral of u du, and that's then a very, very easy integral to calculate. I'll leave the rest for you to read. Next week is going to be our final lecture. We're not doing section 7.4, we're going to move straight to section 7.5, indeterminate forms and L'Hopital's rule, then inverse trigonometric functions, and then we finish the course with hyperbolic functions. Are there any questions?